Okay, so we're going to continue talking about ice tables. So for this problem, we're going to need to construct an ice table. Just make sure you have your notes handy so that you can refer back to it since it was a really long weekend. And so let's take a look at this problem. So we got one for sulfur trioxide. If it's kind of hard to see, this is the equation right here. It's going to decompose and it has an equilibrium reaction. And then it gives you the temperature and the partial pressure, and then it gives you the partial pressure at equilibrium for SO3. Okay, so what we're going to do is we're going to start off by making an ice table. So I'm going to copy down this reaction. And I'm going to cheat because I have the powers of copy and paste and you guys don't. Okay, so you're going to want to copy down this reaction, and then we're going to spread it out a little bit so that we have enough space to make our ice table. Make sure you guys do that. And so what we're going to do is underneath, we're just going to write I for the initial concentration, C for the change in concentration, E for the equilibrium concentration, and then we're just going to fill in all of the numbers that we have. Okay, so I'll give you a second to start constructing this. And if you guys finish early, you guys can start filling in your numbers, or at least the numbers that are given to us. Hey, Jaden, can you do me a favor? Can you go to Pep Peak and ask him if he has the my notebooks, if he took them? Just ask, did you take Mr. O's AP notebooks? You know where Pep Peak is, right? Go through that door. It's the first door on your right. So not this class, but go down the hall a little bit, and there's the first door on the right. Okay. And if he says yes, and if he has them, tell him I charge interest. Yeah, I want his car. Okay. I don't know. Yeah, dude, used cars are expensive nowadays. It's good resale value. Yeah, I could sell my car right now, and I would get more for it than when I bought it new, than the price when I bought it. Guys, it's because Taiwan can't pump out those microchips right now. Who? Me? F-150? Huh? F-150, a truck. Huh? Yeah, dude. I'm a rancher. I put my cows in the back. I'm just kidding. Oh. Weight room, dude. You're saying jump higher into it. Okay, so let's plug in the numbers that we have. Here it tells us that initially that SO3 has a partial pressure of 0.5 atm. So we're going to plug in 0.5 atm for the initial pressure. Okay, and then it tells us at equilibrium the partial pressure drops to 0.2 atm. And it doesn't say anything about the other compounds. He did have them. That thief. No, I'm just kidding. Mr. Pepik, if you're listening, I love you very much. No, Mr. Pepik and I and Mr. Edwards, we went camping together. We're good.
Oh, you want to say the printer was broken?
Oh, okay. Why's the printer broken? I just printed something. Anyway, Mr. Pepik and Edwards and I, we went camping together. And then Pepik had the choice of who to sleep with, and he chose me. Like, there's nothing weird. Two bros sleeping in a tent together when it's camping. Anyway, huh? No, it's not weird. I think it's because I'm smaller than Mr. Edwards. I don't know if you've seen that man, but he's tall, and I'm pretty petite, and so I think he wanted the extra space. Anyway, okay, so we don't have anything, any of the products to start with. And so what we're going to do now is we're going to figure out the change. So the change is what? Yeah, negative 0.3. You got to be careful with those negatives. Okay, now we do need to be careful because of the stoichiometry, right? It's 2 moles of SO3 for every 2 moles of SO2 and 1 mole of O2. And so that means that the change of 0.3 is going to equal 2, and we'll do X. Right, and so the base value of the change is going to be 0.15 atm. Okay, so since we lose 2 moles, per mole is going to be 0.15 ATM. Okay. Oh, this one's the easy one. Good, good, good. Okay. Next, we're going to go to the other compounds. Do you guys think you could finish this up on your own? Okay. I will give you guys 2 minutes to try finishing this up just to refresh your memory. And then after that, we'll move on to the next problem, which is a scary one where we have to use the quadratic equation. So something to look forward to. Yes, use that song. Into it. Okay, so now that we have the base value of change per mole, we can start filling stuff in for the products. So if you notice, SO2 has the same coefficient in front of it, so it's going to have the same value of change. Okay, it's going to be plus 0.3. O2 has a coefficient of 1, which is half of 2. So it's going to be a base value of change. It's going to be the base value, which is 0.15. That means we're going to end up with equilibrium values of 0.3 ATM for SO2 and 0.15 ATM for O2. Okay, that part should have been pretty simple. Any questions on that? Okay, now we got to calculate the KSP. And so what we're going to do is set up our equilibrium constant formula. So the KSP is going to be the products. So the concentration of SO2, but since there's a 2 in front of it, we got to square it. The concentration of O2 and no exponent because it's just 1 divided by the concentration of SO3 squared. Okay, and we're just going to plug in our values into this. Okay, so let me expand it out for you just so we're all on the same page. So we should have 0.3 squared times 0.15 divided by 0.2 squared. Okay, and this time I'm going to calculate it out because apparently I've been messing up a lot lately. And so we are going to get, oops, I subtracted. .3375. Okay, for sure. Yay. 0.33, and I'm going to round it up to 8. And again, no units of measurement because it's equilibrium constant. Okay. So if you got something close to that, should be pretty good. Hopefully you're comfortable working with ice tables. Again, the trickiest part is making sure that you remember finding the base value per mole of change. Okay, just be very careful with the coefficients. All right, you guys ready for the scary part? Yeah. I have been warming you up, scaring you, got you prepared with ice table, and now we're gonna have to do some real math. If it's the easiest part, then I'll be thoroughly impressed. Okay, so if you guys notice, actually, I won't delete that. For the ice table problems that we've been having, we've always started with the initial value and the equilibrium value, right? Kind of, hopefully you make that observation. We start with 0.5, we end with the equilibrium pressure. Now, sometimes they're only going to give you one of them. They're only going to give you the initial. And so you're going to have to create the ice table without knowing the equilibrium value. So let's take a look at an example of that. Okay, so we got 12.20. What I want you guys to do is I want you guys to set up the ice table for this, but don't plug anything in yet. Just set up the ice table. I want you to set up the ice table for this equilibrium reaction. And I want you guys not to plug anything in yet. Just write the ice table. Or draw the ice table. English. It is, but it's also the one I'm best at. Hey, if you can have conversations in that language, I think you're decent. You're good enough. Alrighty, guys. So by looking at the problem, I think some of you guys can already tell why this is going to be irritating to do. But let's plug in the values that we have. It tells us the concentration of A minus, or we're looking for the concentration of A minus for this generic association if the initial concentration of HA is 0.15. So we're going to plug in 0.15 right here. And if you guys notice, that's the only value that we have for this ice table. The only other number that we have is the Ka value. Now, this is helpful because we know that the Ka is going to equal all of the products. So the concentration of A minus, concentration of H3O plus, divided by the concentration of HA, and the concentration. Oh, and water is a pure compound, so we don't even need to include it. So water is not important here. We can just go whook, whook, whook. I almost missed that. Okay, so just to review everything before we move on, we got the ice table. We know the initial concentration of HA, right? That's 0.15. We don't know anything else on the ice table other than that we don't need to care about H2O because it's a pure substance, it's a liquid. The only other number that we have is the Ka value. And we know how to write the formula for the Ka, right? And so what we can do is just set it equal to 1.6 times 10 to the negative 2. And so what we are doing is we're going to be looking for this guy right here, H or A minus, which is going to be in this box right here. This is what we are looking for. Okay. So I'll put a question mark. Okay, this is what we're trying to find. All right, so that's the setup. Any questions on what we set up or what we talked about? Okay, so same thing as normal. We don't have any information about the products, so we can assume that they're all 0, at least in the beginning. Okay, now we don't have the equilibrium value, but we know that in equilibrium, if we don't have any of the products, we're gonna make product, right? And if we're gonna make product, that means we have to put plus. And then if you notice, there's no coefficient, so we can just put plus X for both of them. Okay. If there was a 2 in the front, you would put plus 2X. If it was a 3 plus 3X, right? Same thing that we've been doing. Yeah, just write in the comments though. Resubmit. Can't see. Okay. What that means is at the equilibrium, the concentration will be X and the concentration will be X. Okay, because if you go 0 plus X, it's just going to be X. All right, so far so good? All right, now we're going to get to the part that's kind of annoying. HA needs to decrease in order to produce product, right? So we're going to have to, the change is going to be minus X. Again, that's because the coefficient is 1. If it was 2, it'd be minus 2X. If it was 3, it'd be minus 3X, etc., etc. All right, that means the equilibrium value is going to be 0.15 minus X. Okay. So yeah, it's getting more confusing now because we're not using numbers as much anymore. It's a lot more letters. Okay. But we now have the information that we need to plug in to the formula right here. Okay, so what I'm going to do is I'm just going to plug and chug, okay? The concentration of A minus at equilibrium is what? X. So we're going to plug in X on the top. The concentration of H3O plus is X. Okay, so X times X on the top divided by, what's the concentration of HA at equilibrium? Yeah, 0.15 minus X. And this is all equal to the Ka value, which is 1.6 times 10 to the negative 2. I don't want to write scientific notation, so I'm going to change to 0.016. Okay, so we can take all of that information and then we can plug it into the Ka equation. And if you guys remember, we're still looking for the concentration of A minus. So what we're trying to find still is we're trying to find X. So using this equation, if we can find X, we can get the answer that we're looking for. Does that make sense so far? Okay, so from here, it's just basic algebra. But once you simplify this fraction down, you're going to see that it's going to become a quadratic, and that's where it gets kind of annoying. Okay, so easiest way to simplify this right here is you're going to have to multiply both sides by the denominator. So 0.15 minus x. So I'm going to multiply the right side by 0.15 minus x. Okay, if we do that on the left side, this is going to disappear. And we can also simplify x times x as x squared. Okay, so we have our first simplification of the equation. And I think you guys kind of see where we're going with this. Okay, so here on the right side, we want to distribute the 0.016. And so what we're going to do, I'm going to pull out my calculator, and then we're going to do 0.016 times 0.15. So on the right side, we're going to have 0.0024 minus 0.016x. And you guys can slowly see the quadratic, the beautiful quadratic take shape. Because math is beautiful. Not really. Okay, let's move everything to the left side. So what we're going to do is we're going to keep x squared on the left side. We're going to, in order to move negative 0.016, we have to add it. So it'd be 0.016x. And then we got to subtract this guy right here. It's minus 0.0024 equals 0. And there you go. You guys can see the quadratic, and we need to solve for x. Okay, so before we start doing the math for that, I know some of you guys already know it, and you guys know how to plug it in, but some of you guys might not. So we'll take a break right here. But any questions? Okay. Okay. So before we move on, let's talk about quadratics. So when we want to solve a problem where we have x squared, x, and no x, okay, we have to use something called the quadratic equation. Now, the quadratic equation, easiest way to memorize it, I learned it 15 years ago to this song, and I hope that you guys remember this song as well, because this will be the only time that I sing for you, okay? You can sing along if you want. It goes to the tune of Pop Goes the Weasel, okay? So this is the quadratic equation. It's x equals negative b plus or minus the square of b squared minus 4ac all over 2a. That's what the quadratic equation is, okay? Thank you. I'm trying to be a YouTube singer. Okay, so that's the quadratic equation. Now, if you're unfamiliar with the quadratic equation, basically what it's saying is the coefficient in front of the x squared is going to be a. The coefficient in front of x is going to be b. The coefficient in front of, or that's not a coefficient, but the value with no variable is going to be c. And if we plug it into this formula, we can solve for x. Okay. If you guys forgot, please go check your Algebra 1 notes. It's in there somewhere. Okay. All right. So I'm going to start plugging things in. If you guys feel comfortable plugging this in, please go ahead and do so just so you can get that practice in. But I'm going to start plugging in the values. So x is equal to negative b, which is the value in front of x. So it's going to be negative 0.016 plus or minus the square of b, which is 0.016 squared minus 4. A is going to be 1 because there's nothing in front of x squared. C is going to be negative 0.0024. And then that's going to be all over 2a, which is 2 times 1. So we got a big, fat formula right there that you guys can simplify. I'm going to give you guys a minute to start simplifying it just so that you guys can get a little bit of practice interpreting it. And then I'm going to kind of break it down a little bit. And then I'll explain the last part of the problem. But we're almost done. We just need to plug and chug correctly. Alrighty, guys. So if you're still calculating, please feel free to continue and to finish it up. But I've written out the simplification of the square root. Everything inside the square root should have come out to 0.0993 or something close to it. Okay. Now, we are kind of at this position right now where we need to make a decision because we have plus or minus, right? So in this problem, what we can do is we can either add these two values together or we can subtract. Okay. Now, I'm going to give you guys the values for both of them just so that we can compare. Okay. Some of you guys might have figured out what the right thing to do is. But if we add those two values together, we are going to end up with 0.0417. If we subtract the values, we are going to end up with negative 0.0577. And this is all x equals, okay? Okay, so those are our two options. Now, mathematically, both of those options work. If we're in an algebra class, you did great. You got the two values that you should have gotten. However, we're doing chemistry right now, and chemistry is based in reality, right? Math is a bit more metaphysical, a bit more abstract, but chemistry has to do with what reality is. And so if you guys remember, we're looking for x, right? What is x? What's the unit of measurement for this number? Molarity, okay? So this has to be molarity. Okay, so our numbers are basically telling us it's going to be either 0.0417 molarity or negative 0.0577 molarity. Okay, let's just think about this. Can we have a negative molarity? No, right? You can't have a negative concentration. You can't have negative mass, right? Although it would be kind of cool if I had negative mass. Or you can't have negative moles. You can't have negative molarity, right? And so our value has to be the one that makes sense in real life. And so our final answer is going to be the one that is positive, the one that makes sense, 0.0417 molarity. That is going to be the concentration of A minus. Okay. And that's one problem.
That's not including like the change, like the exponent, or not the exponent, coefficient of the other.
Yes, yeah. So it does get more complicated with this. Okay, which is why we're actually going to be spending a lot of time doing these ice tables. I want you guys to get really comfortable with it. To be honest, if you guys kind of look at the side, we are about halfway done with the unit, but we're not finishing for like another 2 weeks. So the reason I did that is so that we would have some extra time to do some more practice problems. I really wanted you guys to get comfortable doing ice tables because for the AP test, you're just gonna have to be able to do these like in your sleep in order to do well. So we will have some time to do practice problems, and that's pretty much all we're gonna be doing today. So if you don't 100% understand this yet, it's all good. We have a lot of time to practice, but just make sure that you guys are reviewing your notes, trying out extra problems. If you guys go on Google and look up ice table problems, you'll get a bunch, and you should be able to practice them. Okay. All right. Well, we're gonna continue. We're basically gonna do the same type of problem again. So we're gonna move on to 12.21. Anybody still need this? Okay. I am recording this, right? I am recording this, and so if you guys need to, this will be uploaded on mrochemistry.com. Like, comment, subscribe, smash that like button, whatever, and join my Discord, Patreon. Okay, so I have this 5% rule for you right here. Don't write it down. I'm gonna briefly try to explain this for you, but basically, so you know how we did all that stuff for the ice table, right? Okay, for this minus x. There are times when this change in x is so small, you can ignore it. Because if we think about it, let's say the x, instead of this value right here, let's say that the x was 0.00000000001. it doesn't matter. Like that's a rounding error, right? Because it's so small. So if X is really, 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 really small, then we can actually ignore the change. And so we could have actually done the math with just 0.15. And if we plug that in right here, that's just X, and then 0.15, X squared. And it's a lot easier to solve, right? If we ignore the change, right? And so that's what the 5% rule is telling us. The 5% rule is telling us, and now you can write it down, if X divided by the reactant concentration, okay, is less than 0.05, which is 5%, we can ignore X. And that's what this problem is going to be. I'll just let you guys know right now. I'm going to show you guys how to use the 5% rule because it can actually save you a lot of time because you don't need to use the quadratic. You just need to do a simple calculation to test if it fits the 5% rule. And the reason why it's 5% is because when we actually do labs and things like that, experiments with equilibrium and concentrations, 5% is the, shoot, I forgot the word. Margin of error. 5% is the margin of error. Yeah, our measurements will always either be, we have to assume that could be 5% higher or 5% less than the recorded value. Get it together, Mr. O. Losing my mind here. Okay, so with that being said, I'm going to show you guys how to use the 5% rule. First thing we want to do is we want to set up our ice table. So I'll give you guys a minute to set up your ice table for this reaction. And if you feel comfortable filling out the ice table, you can start filling in your values based on the information that we have. Okay. All right, I'm gonna start helping you out. If you guys are still plugging things in, please feel free to finish up. But for the sake of time, I'm gonna start plugging in our ice table. So it's asking us what's the concentration of hydronium, H3O plus. So basically, we're looking for this guy right here. This is what we're looking for when 0.2 molarity acetic acid is added to water. So we know that our initial concentration for acetic acid is 0.2 molarity. Water is a pure compound, so we can just plug in nothing for it. We can ignore this column. And it tells us the Kc is 1.8 times 10 to the negative 6. Okay, so based on this data right here, we know that it's going to be 0 for our starting numbers. We know that the change is going to be minus x right here, so we can simplify that in the equilibrium concentration to 0.2 minus x. We can do plus x here, and that means that the equilibrium concentrations are going to be x and x. And this is the one that we're still looking for. Okay. So hopefully this is what you got for your ice table. Okay, now I did tell you guys that I'm going to show you guys how to use the 5% rule, which means that in this problem, we're not going to have to do a quadratic, okay? So what we're going to do to see if the 5% rule works is we are going to assume for a second, so we're going to assume x is really small, okay? For this box, right, for the change. We're going to assume that x is really small.
So everything's right, but it just doesn't actually
Given 0.5. Yeah, Okay, so we're gonna assume x is really small. Okay, so if x is really small, we can kind of just ignore it. Okay, so we're gonna assume that there's not really a change, right? Because if the change is 0.000001, right? It doesn't really matter if we include that in our calculation. That's a rounding error. So if there's no change, that means the equilibrium concentration is still gonna be 0.2. Okay, and then we know that Kc, the equilibrium constant, is 1.8 times 10 to the negative 6. Okay, we know how to write the equilibrium concentration, right? It's going to be the concentration of H3O plus times the concentration of the conjugate divided by 0.2. Okay. I kind of skipped showing the formula. Does this make sense where we got this equation? It's the concentration of products divided by the reactant. Okay. So from here, I'll give you guys a minute. I want you guys to solve for x. Given this assumption. Just plug it into your calculator. And then after that, we'll go over to see if this passes the 5% rule. Okay, I think you'll like this a lot more than doing the quadratic. All right, so I got x to be 6 times 10 to the negative 4, or 0.0006. Okay, everyone good with that? Okay, so now we can use the 5% rule. So we're gonna see if it was okay to ignore x. Okay, so we're just gonna use this equation right here. We're gonna put x on the top. We said that x is 0.0006. We're gonna divide it by the reactant concentration, which is 0.2. And if the number that this equation spits out is less than 0.05, it's okay to ignore x. Okay, so if you plug that into your calculator, let's see if it was okay to ignore x. Calculator. Oh, there it is. Oh no. Okay, so we're gonna do 0.0006 divided by 0.2, and I already kind of gave you that. I told you it's gonna pass the 5% rule, but it's 0.003. And since it is smaller than 0.05, yes, this is going to pass the 5% rule. Okay, which means that our value for x is really going to be 6 times 10 to the negative 4, which is going to be the concentration of H3O plus. Okay, and it's because it passes the 5% rule. If you divide the x by the reactant concentration, it's less than 0.05. It's okay to ignore x. Okay, a lot easier, right, than doing the quadratic, and a lot fewer places for you to mess up your calculations. Alrighty, any questions on the 5% rule? Ice tables in general? Okay, what we're gonna do is I'll leave it up here for a second, but if you guys have the workbook on your Chromebook or something, we're gonna get started on 12.22. It's okay, I'm gonna bring it up in a sec after I give the instructions, and I'm gonna give you guys about 5 minutes to do 12.22. Okay, I want you guys to interpret it on your own. I want you guys to set up your own ice table. I'm gonna give everything to you guys right now. See if you guys can get it. This will be a good way to see if you guys are ready for these types of problems. Okay, take about 5 minutes. You can work with the person next to you. Did I spell gases wrong? Isn't it 1s? Is gases is 1s, right? It's 1s. Bro, there's no way it's 2.
When you spell gaseous, you use 2 S's. Right?
No. No.
Yeah, you do.
Nah, bruh. It's
It's
1s. Dude, Google's tripping me up. What is
Oh shit.
that? What's this? It's modern English. Modern. Modern, anyway. Ignore all. Okay. Anyway, I'll give you guys 5 minutes. Dude, I need to pause these recordings before I do these weird tangents. It's a waste of your time when you're looking back at this. Anyway, I'll give you guys 5 minutes. Try this out. We'll get the person next to you. See if you can figure out the ice table and solve for everything. And then we'll see if you guys get it. Good luck, guys. Alrighty, guys. Yeah, it's okay. Alrighty, guys. Let's go over this. See how well you guys did. But if we take a look at this problem, so one thing I do want to point out is that this problem is asking for equilibrium concentrations, right? And so you're going to want to end the problem with molarities. Be very careful of what unit of measurement you want to end up with. And so what I did was in the beginning, I did the 2 moles divided by 4 liters because molarity is moles over liters. And that's where I got the 0.5 for the initial concentrations from. If you guys started the ice table with just 2 moles, that's totally fine. Just make sure that at the very end that you divide by the volume, or you're just going to be giving moles, not molarity. Okay, so I have the ice table set up, got the equilibrium concentration, and now we just need to plug in what we got. So the concentration for the products is going to be x times x, which is going to be x squared, divided by, we have 0.5 minus x. Now, what I'm going to do is I'm going to use the 5% rule because I don't want to do this twice, because you're going to get a quadratic and it's going to be a more complex quadratic with a coefficient in front of everything. And so what I'm going to do for this problem is for both of the changes of the reactants, for both of these guys right here, I'm going to assume x equals small. And so if I assume that it's small, I can ignore the x here, ignore the x here, and that way I could just do 0.5 for both of them. Okay. So we're going to put 0.5 on the bottom for both of them. So on the bottom, it's going to be 0.5 squared. Okay. Any questions? I know there's a lot of stuff I went through. If you did the quadratic, you'll get a very similar answer. You just did a lot more work than you had to. Okay. But we don't know that yet. I'm going to test the 5% rule. Okay. So what I'm going to do in order to solve this problem is, if you guys notice, this is squared and this is also squared, right? So what I'm going to do is I'm going to square root both sides. And if I square root both sides, I'm going to end up with the square root of 0.771 being equal to x divided by 0.5. Okay. Again, your calculations might look a little bit different from mine just because we can take a bunch of different steps in order to do it. Okay, but what I'm going to do is, does calculator have square root? It does. Good. Okay, we're going to do 0.771, and then we're going to find the square root of that. That's going to give me 0.878 on the left side. And then I'm going to multiply that by 0.5 so that I can isolate the x. So what I'm going to do is I'm going to times 0.5. That's going to give me 0.439. So x equals 0.439. Did I mess up somewhere? I think I messed up somewhere. We'll see. Maybe maybe the 5% rule doesn't work here. This would be a good example of how to use it. Okay, I'm going to test the 5% rule. So x divided by the concentration. Yeah, this isn't going to work. Okay, 0.439 divided by 0.5. And we can already see just by looking at this, can be a lot greater than 5%. So here we cannot assume the 5% rule. So 0.439 divided by 0.5 is 87.8%. So you can't assume that x is really small, okay? Okay, so here we have to do the entire quadratic thing. We cannot assume x is small here because it does not pass the 5% rule, okay? So that means we have to do 0.5 minus x and 0.5 minus x. That makes sense. Why doesn't match the 5% rule? Okay. So what we're going to do is we're going to erase all this because all our calculations showed us that it's not going to work. And so instead, what we're going to do is we're going to plug in everything for what we got. Okay. So the equilibrium concentration will equal x squared. Same thing on the top because this is x, divided by 0.5 minus x and 0.5 minus x. Now, lucky for us, if you guys take a look at these two, right? They're the same thing, right? So what we can do is we can just erase one of them and just square the other one. And that's going to equal the same thing. Okay. Now, if you guys notice, this is the same setup that we had earlier, right? We can square root, and now we don't have to do the quadratic because we'll have the square root of 0.771. And if I square root this stuff, it's squared and squared, it'll be x divided by 0.5 minus x. And then from there, the math becomes pretty simple. You're just solving for x. Okay. So what you're going to get is 0.439 minus 0.878x equals x. This is what happens when you multiply both sides by 0.5 minus x. And then from there, you can just simplify. You'll have 0.439 being equal to 1.878x. And then you can solve for x, which is going to be 0.234. So that's what you should have gotten for your final answer. We took these values, we plugged it in, and if you actually squared it, it would have been very complicated to do. But since we square rooted both sides, we were able to get rid of one of the x's. Okay. A lot of math. So I know that this time the 5% rule did not work, but I think it's still worth a shot trying to see if the 5% rule will work or not. Okay. A little tip that I do want to give though, you guys notice the KEQ value is 0.771, right? I recommend not using the 5% rule. So if the KEQ is bigger than 1 times 10 to the negative 4, don't use the 5% rule. It's probably not going to pass. You might want to jot that down somewhere. So if the the equilibrium constant is less than 10 to the negative 4, it's worth a shot using the 5% rule. But if it's bigger than 10 to the negative 4, then it's probably not going to pass and you might be wasting your time. Okay. Yeah. No, because you need to divide by 1.878. Let me see. So you're talking about this step right here, going from here to here. Okay, let's check it out. 0.771 squared is going to be 878. So let me, just so that we can have some bookkeeping, 0.878, and then you'll have to multiply that by 0.5. So 439, that's correct. Yeah, because you'll have to distribute. So 0.5 minus x, and then 0.5 times 0.878 should equal 0.439. Yeah, let me know, because I do make mistakes a lot, as you guys know, but that's going to be x. Any other questions? You guys look so tired now from all this. Okay, so we're still not done technically because it's asking for the equilibrium concentrations of all 4 gases. Now we have x, and CO and H2O, the concentration is just going to be x. So the concentration of CO and the concentration of H2O is going to equal 0.234 molarity. However, for the concentration of H2 and the concentration of CO2, we're gonna have to do 0.5, excuse me, minus 0.234. And so you should get concentration of 0.266 molarity for H2 and CO2. So if you guys were able to get both of those answers without me, wow, that is, you are on track. Yeah. Mm-hmm. Around within 5%. Yeah. What did you get? 0.25? Oh, you're good. Yeah. Yeah, that's why I personally recommend 3 numbers after the decimal for everything, because that keeps it within 5% most of the time. There is a unit called, what is it? Significant figures that we skipped at the beginning of the year. That's the actual real way to do it. But there's like, I think it's kind of a waste of time. Yeah. Yeah, it's irritating. All right. Any questions? Okay, let's take a 7-minute break. So we'll be back at 10:40. You guys can use the restroom, stretch your legs, get some water, and then after that, we'll come back to our last problem for today, and we should be all done. Let's take a break. Okay, guys, let's I guess go into our last problem for the day. We're gonna go to 12.23. So again, today's just basically ice table day. So I want you guys to take some time, work on 12.23. See if you can finish it up on your own. Again, if you want to work on it with somebody else, I'm chilling with that too. But I'll give you guys 6 minutes to try this one. Write the ice table, do everything you got to, and then we'll double check our answers in about 6 minutes. Okay, good luck, guys. Okay, let's finish up with this problem. So I have the ice table for you. I have the KSP equation. What we want to do probably is try to test the 5% rule. So what we're going to do is we're going to start off by assuming that X is really small for the reactant. So let's plug it in, see if it passes the 5% rule. And then if it does, then we can move on. If not, we're going to have to do the quadratic. Okay, so what I'm going to do is I'm going to write the equilibrium constant, 1.2 times 10 to the negative 5 equals, we got 2x for NO. Got to square that. We got x for O2. On the bottom, we're going to have 0.25, and then we're going to square that. Okay, so I'm going to kind of skip a couple steps here, but if you simplify this out, you should get 7.5 times 10 to the negative 7 equals 4x cubed. Basically, what I did was I multiplied both sides by the denominator, and I simplified the top. Okay, and then if we simplify that out even more, we should get x is equal to 0.0057. Okay, and then from here, we can test the 5% rule. So what I'm going to do is I'm going to put 0.0057 divided by 0.25, the reactant concentration. And that should give you a value of 0.002. And this is going to pass the 5% rule. Okay, so basically, I just made sure that passed the 5% rule. Okay, so here, we can just say this is x. We don't need to do the quadratic because x is so small, it's less than the 5% margin of error. Okay, and then we're done. We just need to find the equilibrium concentrations. Oh, I forgot to mention too, I got 0.25 because I divided 0.5 by 2 for the molarity. But if you guys used 0.5, just make sure that your x that you divided by the volume, which is 2, and that should give you the same numbers. All right, so for the concentration of NO2, all you got to do is plug in your value point. You could actually just write 0.25, but if you want, you can do 0.25 minus 2x. So 0.25 minus 2x, and that'll give you a concentration of 0.2386 molarity. That's your concentration of NO2. For your concentration of NO, you're just going to do 2x. So 2 times x, that should give you an answer of 0.0114 molarity. And then for your concentration of O2, it's just gonna be X, which is 0.0057 molarity. And there you go. If you guys were able to get that on your own, great work. That was kind of a trickier question, just because it got a little bit confusing with the power of the variables, and you have to test the 5% rule. But if you guys got it, great work. Yeah, what's up? So you will be on the FRQ question, but everything on the MCQ, it's not going to be anything too, you're not going to be doing this. Yeah, good question. But if you want to check requirements for calculators, I think they have a list of, what is it, acceptable ones and unacceptable ones on the College Board website. All right, any other questions, guys? All righty, guys, that's going to be pretty much it for today.